Okay, last lesson we were looking at creating new polynomials made from a combination of the roots. And here we've been discussing z to the 7 minus 1 equals 0. So we've been up here discussing this one. And we got all its roots, which, as you know, were all these ones here: cis 2 pi on 7, cis 4 pi on 7, and so on, 6 pi on 7. So we got all the roots of it, and we can name one of the roots w, or omega, and it's the root with the smallest positive principal argument. So we can name that one there omega, and that's cis 2 pi on 7. And then the other roots can be related to that root. So cis 4 pi on 7 is just omega squared, or w squared. I'll call it w, right? It's just w squared. And we've got w cubed for the next root, and so on. So we were up to working with those roots of z to the 7 minus 1. And today we're going to create a new polynomial from some combination of those roots. And we've chosen a polynomial we're going to make, which will be a cubic, because it's got three roots: 1, 2, and 3. W plus w6, w squared plus w5, and w cubed plus w4. That's the three different roots that we've got for this new polynomial. And because it's a cubic, if we can find the sum of the roots taken one at a time, which is usually called the sum of the roots, the sum of the roots taken two at a time, and the sum of the roots taken three at a time, which we normally call the product of the roots, well, then we will know what is a polynomial that would have those roots. I say a polynomial because it's not the only polynomial, the only cubic that we'll get. Any multiple of that cubic will also have the same roots. But let's just find a new polynomial with those roots up there. So the first thing is, what would the sum of the roots be? And that's what we got up to last time. And the sum of the roots is the first root, which is w plus w6, and the second root, which is w squared plus w5, and the third root, which is w cubed plus w4. And when you add them all together, you get minus 1. Now, we know the reason for that comes from when we did actually factorize z to the 7 minus 1 before, we got z minus 1, and then we got 1 plus z squared plus z cubed plus z4 plus z5 plus z6. We got that as our factorization for z to the 7 minus 1, which meant that if if w was a root, then we could say that either w minus 1 could be 0, or 1 plus w squared plus w cubed plus w4 plus w5 plus w6. That could equal 0 if z to the 7 minus 1 has to equal 0. When you sub it in, if it had to equal 0, then that's what would be the case. Now, we know that w was not 1, because 1 doesn't have a positive principal argument. The argument of the number 1 is 0. So w must send that second set of brackets to 0. In other words, that second set of brackets equals 0. 1 plus w squared plus w cubed plus w4 plus w5 plus w6 equals 0. Therefore, all that stuff must equal minus 1, which is what I've said up here at the asterisk stage. So that's where we got up to last time. We were saying that the sum of the roots for our cubic that we're creating is equal to minus 1. And remember, the sum of the roots is minus b on a. I'm saying we've got some polynomial a z cubed plus b z squared plus c z plus d. We've got this polynomial, and we know the sum of the roots from that polynomial is minus b on a. So far we've found that minus b on a is equal to minus 1. Now the product of the roots. Well, we've been given these three roots, w plus w6, w squared plus w5, and w cubed plus w4. So we need to multiply those together to get the product of the roots. And I'm saying it equals 1, but let's have a look why that is. So let's multiply it all out. First of all, let's multiply the first two brackets together. We get w cubed plus w6 plus w8 plus w11. And we've still got to times that by the last set of brackets. So we're talking about w6 plus w7 plus w9 plus w10 plus w11 plus w12 plus w14 plus w15 when you multiply them out. And we know, because w was one of the roots, the one with the smallest possible positive principal argument, but it sort of doesn't matter, it's a root, then it solves w7 equals 1. So anytime you see w7, clearly you get 1, right? So this is w6 plus 1 plus, now this is w7 times w2, isn't it? w9 is w7 times w2, and w7 equals 1. So instead of writing w9, I can just write w2. w10 is w7 times w3, but w7 equals 1. So instead of writing w10, I can just write w3. And for w11, it's w7, which is 1, times w4. And for w12, it's w7 times w5. So it's just w5. w14 is w7 squared, which is 1 squared. What's 1 squared? 1. And w15 is w7 squared, so w14, which is w7 squared, times w, which is 1 times w, which is just w. So you can see that altogether here I've got 1 plus w plus w squared plus w cubed plus w4 plus w5. I've got all that, plus w6, plus I've got another 1. And we know that the first part of all of that, we know that if you take all of that I'm circling there, that is 0. Because we know it from over here that equals 0, which means we've got 0 plus 1, which equals 1. So the product of the roots, as we said before, the product of the roots is equal to 1. So the sum of the roots was equal to minus 1. The product of the roots, which is the sum of the roots taken 3 at a time, but there's only one way to take 3 at a time. The product of the roots is 1. And now we just want to find the sum of the roots taken 2 at a time, because that's going to be C on A. Up here at the top right of our screen, we see we've got C in front of the Z there for our third coefficient, and we know that the sum of the roots taken 2 at a time is equal to C on A. So let's take them 2 at a time. So I've done that one times that one, and then the first root times the last root, and then the two middle roots times together. Now I'm claiming that equals minus 2, if we go through that process of expanding all that out, remembering that W7 is equal to 1 because W is a root, then we should be able to get that minus 2. Let's do it. We expand the first two sets and we get W3 plus W6 plus W8 plus W11 plus W. Now we're on to the second set of brackets. This is W4 plus W5 plus W9 plus W10 plus the last set of brackets is W5 plus W6 plus W8 plus W9. And I'm reckoning that equals minus 2, but let's show why that is. So I'm going to leave W cubed alone and W6 alone. But W8, that's W7 times W. So that's 1 times W. So I'll just replace it with a W. W11 is W4, isn't it? Because it's W7 times W4, and W7 is 1. There's W4, W5. W9 is W7 times W2. So 1 times W2. W10 is W7 times W3. We've got W5, W6. W8 is W7 times W1. And W9 is W7 times W2. So when I look through here, I can see I've got a W there and also a W there. And I've got a W squared there and also a W squared there. And I've got a W cubed there and I've got a W cubed there. Have I got a couple of 4s? Yep. Have I got a couple of 5s? 5, 5. Yep. Have I got a couple of 6s? Yep. So basically, I've got 2 of the following. I've got W plus W squared plus W cubed plus W4 plus W5 plus W6. Now, from before, right, up here, we know that W plus W2, 3, 4, 5, 6, that equals minus 1. So 2 of those is minus 2. So now I've managed to get myself the sum of the roots being minus 1, the sum of the roots 2 at a time being minus 2, and the product of the roots, the sum of the roots 3 at a time being 1. So I'm basically saying let A equal 1, because you could have any value of A you like, and we might as well let it equal 1 because it just says find a polynomial. And we know that minus b on A, which would be minus b on 1, is equal to the sum of the roots taken 1 at a time, which is minus 1, so b equals 1. We know that c on A, c on 1, is equal to, and what was the product? Oh, sorry, minus 2. And we know that minus d on A is equal to the product of the roots, which is up here we got the product of the roots was 1. So minus d is equal to 1, because we said let A equal 1. So d is equal to minus 1. So you can see why I put d is minus 1 there. Why oh, hang on a minute. Why I said c is minus 2 can go there, and why I said b is 1 can go there, just plus 1 in there. And I've created a polynomial that's a cubic, and I know its roots will be w plus w6, w squared plus w5, and w cubed plus w4. And those are actual roots of that polynomial. So, for example, w plus w6 is, when you look up here, w is cis 2 pi on 7, and w6 is cis minus 2 pi on 7. So one of the roots is cis 2 pi on 7 plus cis minus 2 pi on 7. And they happen to be conjugates, so we know, hey, when you add cis pi on 7 and cis minus 2 pi on 7, you get twice cos 2 pi on 7. So in fact, one of the roots of that polynomial we've created is 2 cos 2 pi on 7. And you could work out the other roots of that polynomial as well. They're actually numbers you can put in the calculator and get a decimal number for. So that's one thing you can do when you've worked with something like all the roots of unity in terms of the seventh roots of unity. You can then use those to create some other type of polynomial by pairing them up, for example, like we did. Now, sometimes you can even take it a bit further and work out some exact values. It's a bit hard, like with that last question there, with that last polynomial we just found, with the last polynomial we just found, which is this one here. How do you actually solve that? Like, it's not like there's a quadratic formula that we can use here for cubics. There kind of is, but not. We don't know it, and it's not going to apply to this one. But it's not that we can just solve that bad boy. So we sort of end there. We find we could find the three possible roots. They might even be real numbers that we could use, but that's about where we end. But if it's a quadratic, like we're going to talk about now, we could go through that whole process that we just went through. And also, we could say, why don't we actually take the quadratic that we end up with and try solving it using the quadratic formula and come up with some sort of values, and maybe we can equate together the two answers we get. And that can give us some exact values of trig ratios. So let's give that a go instead of creating a cubic. So I've got the z to the 5 plus 1 equals 0. And I've already worked out the roots there for us, which are minus 1. Cis pi on 5, which would be our omega. Cis 3 pi on 5. Now, if I was to square cis pi on 5, what would I get? That's right. I'd get cis 2 pi on 5, right? But the next one around is cis 3 pi on 5. So this one around here is actually omega cubed. Okay. If I was to power omega up to 4, what would I get? I'd just get cis 4 pi on 5, wouldn't I? Well, that's not one of the roots. Cis pi on 5, what do I have to power that to get out there at minus 1? That's right. It's omega 5. That's omega 7. That's omega 9. But what if you want to go backwards, though? You don't want to talk about it in terms of 7 and 9. How would you go backwards? What would W9 be? Is it W minus 2, for example? Is it W minus 4, for example? What is it? So W0 is 1, isn't it? That's got to be the case. But what's W minus? Okay, that's W minus 1. And what's W7? Someone's looking and going, well, isn't that a conjugate of W cubed? So wouldn't that be W minus 3? And I'm like, yep, that's right. Okay. Anyway, we've got those roots of z5 plus 1 all related to each other by calling the one with the smallest positive principal argument, the cis pi on 3 one, cis pi on 5, we're calling that one omega, and then we can relate all the others to that one. And we can find a quadratic with roots w4 minus w, w squared minus w cubed. So there's its two roots. And we can find the quadratic with those roots by considering the sum and the product of the roots. Now, just out of interest, W4, it's not exactly appearing on there at first look, is it? W4. But did you know that W4 is W5, which is a root, like W is a root of Z5 plus 1 equals 0. So W5 is minus 1, right? It's W5 times W to the minus 1. So that's minus of W to the minus 1, isn't it? So W4 is actually minus of one of the roots that we know. And can you see that if we just look at that a bit better, that's actually minus of W minus 1 and minus of W, right? So in a way, we're kind of adding them, like it's minus of W minus 1 plus W. And the W minus 1 and the W, as you can see here, these bad boys are conjugates, right? So, we'll be able to get something out of this. It's minus, and then it's like 2 cos pi on 5, isn't it? Because when you add two conjugates, you get twice the real part. So there's some logic to them using W4, even though that's not something that's appearing on the roundabout there that I just labelled. I could put it on there, but there is a way to show it. W3 is on there. What about W squared? Can you see where that would come from? W squared. And you just go, yep, W squared is the same as W5. And I need that because I know that's minus 1 in this case. W5 times W minus 3. And of course, W minus, so that's minus 1. And of course, W to the minus 3 is just that root over there. So we are relating together the W3 and this one over here is the minus of W squared. We're relating them together. And since in this we didn't add them, we decided to subtract. That'll help us because W squared is minus of W minus 3. And then we minus off W3, so it's minus of the sum of them. And that's the sum of a couple of conjugates, so it's minus of 2 cos, now W cubed is 3 pi on 5. So there's some logic to them wanting to use minuses when it's a question about Z5 plus 1 equals 0. Because it's a little bit different to when it's Z5 minus 1 equals 0, as you've just seen. All right, now we want to find just two things. Because there's only two roots here that they've given us, we want to find the sum of the roots and the product of the roots. And then we'll have our quadratic with the minus b on a and the c on a business. So the sum of the roots. If I add together W4 minus W and W squared minus W cubed, I get what I've just ticked there. That's the sum of the roots. All right, now that geometric series there, 1 minus W plus W squared minus W cubed plus W4, and you might say, how come you've just thrown an extra 1 in there? Go with the flow here. I just want to talk about that series, which is very closely related to what I just ticked. That series is a series with A equals 1 and R equals minus W, and N is equal to 5. There's 5 terms there. The W's go from 1, 2, 3, 4, and there's the 1 there. So basically, we can add up that series, and we're like, oh, that's like W to the, close that. You know, the formula on the formula sheet is a, so 1, r to the n, minus 1 to the 5, minus 1 on r minus 1. Okay, so that's the same as minus w5 minus 1 on minus w minus 1, which is the same as minus of w5 plus 1 on minus of w plus 1. All right, so what we're saying there, let's create myself some room up the top here. We're saying that this series 1 minus w plus w squared minus w cubed plus w4 can be summed up to be w5 plus 1 on w plus 1, which means timesing both sides by w plus 1, we get 1 minus w plus w squared minus w cubed plus w4 equal to w5 plus 1. Now, remembering where these roots have come from, that like we've got two roots we're using here to make a new polynomial, but the roots we're using are made up of combinations of roots from z to the 5 plus 1 equals 0. So this w, it solves w to the 5 plus 1 equals 0. So when w is subbed in to there, you get 0. And since w is not equal to 1, like 1 is the special root that solves into that brackets for z plus 1, since w is the root with the smallest possible principal argument, it solves this bad boy here, this second set of brackets equal to 0, which means that all that equals 0. So if you're trying to find what's the minus w plus the w squared minus w cubed plus w4, you know that that must be equal to minus 1. Now, possibly, to be technical, I should have talked instead of about w there when I was doing this series here. I should have used z and then substituted in w. But I think you get what I'm saying, and you get why I added that extra 1 into there, even though that's not what I was looking for a minute ago, just so I could show you again where that comes from. So that little statement that I've circled, and I'm super asterisking now, the sum of the roots, we've just shown that the sum of the roots is equal to minus 1, right? I'll just write that next to it so we remember the sum is minus 1. All I need is the sum of the roots and the product of the roots. All right, so I think I've just talked through that fact that we know that that equals 0 and therefore that equals minus 1. So we're moving on. There's the product of the roots. I've expanded out root 1 and root 2 times together to get this statement here. And then I've just claimed magically that it equals minus 1, but it's not magic. Remember that w5 equals minus 1 because w comes from z5 plus 1 equals 0, i.e. z5 equals minus 1, and w is a root of that, so w5 must equal minus 1. So see, w6, that's w5 times w, and w7 is w5 w squared, and w3 is w3, amazing. And w4 is w5 times w minus 1, if you like, or you can leave it as w4 because we've actually got a relationship for that one. So wherever you see a w5, that equals to minus 1. So this is minus w plus w squared minus w cubed plus w4. And when we look at that, we've done that a moment ago up here, and we know that minus w plus w squared minus w cubed plus w4 equals to minus 1. So it wasn't magic. The product of the roots is minus 1. So I know what my polynomial is, z squared plus z minus 1 equaling 0. And the reason is because let a equal 1, because we just want a polynomial. So you could have it any multiple of this one, but let a equal 1. So minus b on a is equal to the sum of the roots, which is minus 1. And a is 1, so it's just minus b is minus 1. So b is 1, hence I get my 1 there. And c on a is minus 1, so c is minus 1. And that's where I get that minus 1 there from. So now we know the roots of that equation are w4 minus w, and I've said we already know that, right? We created that from that. So we know that those are the roots. But look, that equation, when you're in year 10, you would have solved that using the quadratic formula, that z squared plus z minus 1 equals 0. And you would have said z equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. So you would have got minus 1 plus or minus root, and that's 5 on 2. So those are the two roots, minus 1 minus root 5 on 2, which I know is negative, and minus 1 plus root 5 on 2, which I know is positive. Okay. Now, did you know that the value of w4 minus w is the same as w5 w minus 1 minus w, which is minus 1 times w minus 1 minus w, right? Which is w minus 1 plus w. So you've got a pair of conjugates, w minus 1 and w. I'll just go back up and show you there. Circling in purple, w and w minus 1 down there, right? They're conjugates. So when you add them, you get 2 cis pi on 5, twice the real part, right? That's equal to 2 cis pi on 5. And these two guys, they're the same. They're conjugates. So you get 2 cis 3 pi on 5, right? Not cis. What did I mean? Cos. All right, cos pi on 5 is positive. Cos 3 on pi on 5 is in the second quadrant, so it's negative. So the 2 cos pi on 5 is equal to the positive 1. And 2 cos 2 pi on 5 is equal to the 2 pi on 5? I reckon 3 pi on 5. Yep. 3 pi on 5. That should be a 3 in there, is equal to the negative version. So cos pi on 5 is equal to minus 1 plus root 5 on 4. And cos 3 pi on 5 is equal to minus 1 minus root 5 on 4. We might take a break there, having made some new polynomials from roots of the other polynomials, and then we're able to, for a quadratic one, actually work out what's the exact value of a trigonometric ratio like cos pi on 5. That's pretty cool, because if you stick it in your calculator, I won't finish that statement because maybe these days if you stick it in your calculator it does tell you what it is. All right, I'm just going to stop that recording now. We'll do the rest of this sheet on another recording.